G'day, and welcome to TD Physics as we explore relative motion, river crossings at 90 degrees.
Today's story comes to us from the Rhine River in 1945. The Rhine River starts up here in Switzerland, just north of a little place called Liechtenstein. And that Rhine River acts as a natural boundary between Germany and its neighbors as it flows towards the northwest, ultimately to the Atlantic Ocean. As we get closer to this region, between Holland and Germany, we find the town of Nijmegen, where the Canadian troops wintered over 1944 to 1945. And then in March of 1945, in a region between Ries and Wessel, the Canadian 3rd Division joined the Brits and the Americans as they stormed across, making a bridgehead approximately 20 kilometers long on a river that was approximately half a kilometer wide. This is where our story begins.
One of the difficulties in studying relative motion is a lack of experience moving in fluids that are moving. On land, the direction we point is the direction we go. But in a fluid in relative motion, the direction that we are pointed, our heading, is different than the direction our boat or our plane would actually go, our bearing. Let's see what that will look like in the lab, with our robot acting as our canoe and the tarp acting as the stream. Let's see that in slow motion. When our canoe starts paddling, it's pointed slightly upstream. That's our heading. When the river starts to move, it results in our robot canoe heading due south. That's its bearing, represented by the purple line here. How do we do that? We're adding two velocities together. The first velocity, represented here in red, is the velocity of the canoe in still water. If the water didn't move, that's where it would go. Plus, the river's velocity in blue results in the net velocity, or the canoe's velocity relative to the ground, in purple. So how do you cross a Rhine River? Cue the dramatic, old-style music.
Under cover of a colossal smokescreen, British and Canadian troops of Field Marshal Montgomery's 21st Army Group prepare for the war's most momentous victory, the crossing of the Rhine on the Wesel sector.
In addition to smoke shells, they burned 2 million liters of fog oil for an entire week, making a smoke screen 30 kilometers long, the biggest ever in history. The huge Lancaster bombers sent out 8,000 sorties, dropping an inordinate amount of explosives on the surrounding countryside.
RAF rocket-firing Typhoons paralyzed enemy resistance in the vital Wesel area. One lonely farmhouse had been converted into a German HQ.
4,000 artillery pieces opened up for 4 hours, and if they fired 4 shots every minute, that would add up to nearly 4 million shells, the largest bombardment of the war. So under the cover of smoke and an intense barrage, they went across. What did that look like? Pay attention to the direction of the water and the boats.
And what of the men who made the assault in amphibious vehicles across that river, which has been Germany's shield for generations? All services are writing illustrious names in the last page of this war.
Instead of operating through surf, maneuver their craft to and from landing spots in currents ranging from 6 to 10 knots. infantrymen, engineers, and seamen working in close harmony clearly showed the excellent results of their joint training. The unified action resulted in one of the smoothest river crossings in the Continental Campaign.
And a grateful Dutch people reenact this crossing to remember.
Natuurlijk dat we net als 75 jaar geleden ook uiteindelijk de oversteek kunnen maken en de Duitsers daar kunnen verdrijven.
This is from my grandpa's memoirs. The Canadians in Italy were brought up to the Western Front in March, and the 3rd Division made a crossing across the Rhine River and established a bridgehead. Let's go see how they did that.
So again, as we look at some of the physics behind relative motion crossing a river at 90 degrees, just a reminder that the direction that a boat is pointing is called the heading. But if the river is moving, the direction the boat is actually traveling is called the bearing. So if we're looking at the Rhine River, and that time I believe it was actually going faster than this, but the unfortunate part of doing primary research is that it seems that the river was going too fast for our specialized boats to actually do a corrected river crossing. So I fudged the numbers a teensy bit to make this work. So if the river is going 8 kilometers an hour towards the west, we have 2 options. One is we point our boat straight across, and as a result, we head downstream. The other option is we could point our boat slightly upstream, fight the current, and as a result, go directly across. So we're going to look at both of those scenarios right here. The first one, pointing directly north and allowing ourselves to go downstream a little bit. So as you've seen, they crossed in these really crazy landing craft called Buffalo. Another version was called the Alligator, and they could go almost 12 kilometers an hour in still water. So if the river is traveling at 8 kilometers an hour west, and we're capable of going a little bit faster than that at 12 kilometers an hour, what would the resultant be in this case? Well, I can't do this in a perfect scale diagram right here, but if our river was traveling at 8 kilometers an hour west, and our Buffalo, or modified landing craft, was going a bit faster at about 12 kilometers an hour, then what would result is your landing craft heading downstream. Okay, so if this is the velocity of the water relative to the ground, and this is equal to the velocity of the boat, or the Buffalo, in still water, what would actually happen is we'd have a boat facing north, but going actually in this direction where our green line is indicated here. So I'm going to show you some high-tech animation here using Camtasia. So if this is our Buffalo, they had a slightly tapered front to them. So it's going to look a little bit like a bullet. So if we put this Buffalo in the water, it would face north, but it would actually travel in this direction across the stream. That was some pretty amazing animation. So there we go. Let's see it again. So facing north, but traveling north so many degrees west. So we're going to make that lovely boat go away. And we're going to work through this mathematically. So you can see here that if that's our triangle that we have made, then this is a 90-degree angle right here. And we know everything about our water moving, and we know everything about our boat moving if there was no river. And we know neither the magnitude nor the direction of the velocity of our boat relative to the shore, to the ground. But we can figure this out. This would be Pythagorean Theorem. So the velocity of the boat relative to the ground is going to be equal to our other sides here. Dispense with the fancy color notation here. So 8 squared plus 12 squared is going to be equal to the velocity of our boat relative to the ground squared. If we punch this into our calculator, 208 The square root of 208 is 14.4 kilometers an hour. Okay. So again, that is the square root of 208. That's where we got that from. Okay, so we've got a velocity. So this thing is going to be traveling faster because it's got two components, two velocities that are added together. But the one thing we don't have yet, remember that this is a vector. Sometimes in physics we write an arrow over top of our velocity, or our v here, to remind us that we're not done yet. If the angle is unknown, we can figure that out. If this is our angle, tan of theta is equal to our opposite, velocity of our water relative to the ground, over our adjacent, velocity of the boat relative to the water. Okay, so that's going to be inverse tan of 8 divided by 12. So inverse tan of 8 over 12 is equal to 34 degrees. Okay, so that would be north 34 degrees towards west. So that is the resultant velocity. So that's part 1. Number 2, how long would it take to get across? Okay, so this is answer number 1. Here, number 2, the equation itself is pretty easy. The tricky part is getting the right vectors to combine. So how long does it take to get across? Well, time is equal to displacement divided by velocity. And normally we skip this in my class, little arrows, but I really want to include them this time because direction matters. If I told you that I lived approximately 40 kilometers north, 10 degrees west of the school, and I told you that I was leaving, driving due south at 100 kilometers an hour, how long would it take me to get home? Well, if I asked that question, you'd probably try to gently get me some extra professional help and say that doesn't make any sense. And yet on a test under stressful environments, students will do that sometimes. Heck, teachers can do that at times. So for displacement to get across our river, just remember that this was approximately a 500 meter wide stream. We got that from earlier in our video. And our velocity, well, to cross it, that is north, 500 meters north. But we have 3 velocities here. The water's velocity relative to the ground, the velocity of our boat relative to the water, and the velocity of our boat relative to the ground. So which one do we use? The important one on this one is if the displacement that we're talking about is north, then the velocity that you're working with also has to be north. So it's going to be this one. It'll be 12 kilometers an hour. Now notice that we have meters and kilometers here in the same section, so we got to make one or the other match. So I think it's just going to be simplest to call the half a kilometer just as it is. 0.5 divided by 12 is equal to approximately 0.042 or so. Now the hours. Put that into a different perspective. That would take about 2.5 minutes to get across, if indeed it could do this. Okay, so if that's the case, how long or how far downstream would they end up going? And we have 2 options with this. We could either recreate this triangle, except using displacements in this case, because the angles are going to be the same. So we could use this angle here, and we could put 0.5 kilometers on this side, calculate how far downstream at an angle we'd go, and we could use that, would be one method. And then we could also find out how far downstream we went. That'd be one option. But there's actually a simpler option right here, and it's this. Distance is equal to velocity times time. And we want to know how far it went downstream. So if you know the stream's velocity, or in this case the river's velocity, it's going 8 kilometers per hour, and we're in the water for 0.042 hours. Well, we're going to find that. Now, it'd be about 8 times 0.042. So we'd find ourselves downstream about 0.336 kilometers, or about 1/3 of a kilometer. Not a big deal if you don't care where you're landing, but during an amphibious assault, knowing where you're landing is a really big deal. A number of those far shorelines have been particularly well prepared, either by bombardment to clear it of enemies, or some research have been done to figure out where's the sturdiest ground that we can make the best progress on. So, if you're trying to cross the Rhine River here, and you pointed your boat directly across, the result would be you going downstream at an angle, and you would end up downstream. Our second scenario is going to look at what would happen if we corrected for it instead, so we go directly across. And what is the problem where we want to correct for the stream? So we know that our stream is pointing at 8 kilometers an hour west. We know that our boat can travel at 12 kilometers an hour in still water, but in this case we want to point it upstream, north, some east, so that we can ultimately go north. These are a bit trickier in that there's two aspects of these that are not completely known. A strategy I use for this is that if I don't know two things, I quickly draw a line, a reference line here, for my bearing. That means this is the way I want to go. I want to go north. This means that both of my vectors, my velocity arrows, when I add them together, must start and ultimately end when added together on this line. So how I like to think of it is, I know the water is traveling at 8 kilometers an hour towards the west. If that's the case, how fast do I need to go to correct for that? Well, it kind of depends on my angle and how fast I go. If I'm going to be traveling at 12 kilometers an hour, I would make sure that my line here was 50% longer if I was doing it to scale, and I would add it like this. So the velocity of the water relative to the ground, so this side is equal to 8. This is the velocity of the boat in still water. So if the water wasn't moving, it would end up here. But because the water's moving, it's aiming at the water that's right here, and by the time it gets to it, that water will have moved downstream to this location, ultimately resulting in a boat heading due north. So the velocity of this side of the triangle is 12 kilometers an hour, but the direction we don't know. This is the heading. We need to figure out how many degrees north, so many degrees east this is going to be. And you'll note that our resulting velocity right here, relative to the shore, is going to be slower than it would be in still water because we're fighting the current a little bit. So I don't know how big this is in kilometers per hour, but I do know that it is north. This is a right angle triangle, and so solving for this is not going to be particularly fancy in terms of math, but setting up the problem is quite important for physics. It was also quite important for the captains, or coxswains for those who are going to be really picky. Small boat coxswain, big boat captain. What is the resultant velocity going to be? Well, that's just going to be Pythagorean Theorem. I'm going to start off with that, the resultant velocity. So that's going to be, well, two sides, each squared are going to equal 12 squared. So the velocity of the boat relative to the ground squared plus 8 squared is going to equal 12 squared. So the velocity of the boat relative to the ground, 12 squared is 144, 8 squared, 64. And so when this comes to the other side, it becomes negative. And so we're going to end up with 80 here. And so if we take the square root of both sides, we find the square root of 80, 8.94 or so. Sorry, almost mixed up my units there. Kilometers per hour. But we already know the direction. This is north. Done. So number one, the resultant velocity across the river. It's 8.94 kilometers per hour. And how long does it take to get across? Well, again, be careful on this one. Time is equal to displacement divided by velocity. I'm going to be picky here and throw some little arrows to remind me that the direction here matters. And so if this is our displacement, remember that the Rhine River at this location is approximately a half a kilometer wide, and that direction is north. If I'm trying to go north, I need to find my velocity that is north. 8.94 kilometers per hour, and this is also north, will give us a resultant that's going to look like this. 0.5 divided by 8.94. This is going to take us longer than the other trip did, 0.056 hours, or somewhere in the ballpark of 3.5 minutes. In both cases, it actually took a bit longer than that to get across the river, according to the records, because the stream was quite a bit faster, and our boats weren't quite as fast as I put here. They're a fraction less. Nonetheless, this is slower than before, or it took longer than before because we're going slower than before. Some of our energy is going to fighting the stream. Final piece, what is the heading going to be? Okay, so I did this slightly out of order. We're going to do the heading right here. That's going to be number 3. Well, that's going to be this angle right in here. So the order doesn't really matter that much in that these are independent of each other. So if I want to find this angle, now I know all 3 sides, but my recommendation is that if you know these 2 and the other one's a calculated value, now this is Pythagorean Theorem. This should be fairly well mastered by grade 11, and you can check your scale to get an approximation if it's true. But I know these 2 values for sure, so I'm going to use, this is the opposite over here, and this is the hypotenuse. So if we look at SOHCAHTOA, if we have our opposite and we have a hypotenuse, that'd be sine. So sine of our angle is equal to our opposite over our hypotenuse. So this would be the inverse sine of that. Okay, taking a quick look at our diagram here, should be kind of more than 20, less than 45. And a decent scale diagram is a pretty solid plan. By the way, it checks silly mathematical errors that you might make under stress. So this is about 42 degrees. And this is an important thing to note, that the angle that we're using to correct for this, I should put proper formatting here. This would be north 42 degrees to the east. So this is completely answered, but I want to go back to question number 1 just real quick to show you that just because we figured out the angle downstream before, let's go look at that. Notice that that was 34 degrees right here. You can't just grab that 34 degrees and plug it in down here and say, we'll just go the opposite side. The triangle is different and your angles are different. So don't make that common mistake that is often made in physics of assuming that you can just transfer angles from one scenario to the other. So that is how we would get across the river with a correction. We'd point our boat somewhat upstream, and this angle is going to become greater and greater the closer the 2 velocities are together. And ultimately, this problem can't be done if our boat is slower than the water.
So how does the story end for this good-looking soldier from the Essex-Scottish in the Canadian 2nd Division? They got to go across on a pontoon bridge that the engineers built, made with planks going from one pontoon to the next, the trucks going across only a few yards separating them, and they walked beside them with no guardrails, pontoons tipping in all directions, and a couple days later, they walked into Holland on Easter. They walked across on a bridge like this. You can see those narrow planks and nothing separating them from a pretty bad day if they fell off. Private Ross Robinson was awarded the War Medal, the Canadian Volunteer Service Medal, and the France Germany Star, and missed out on the 39 to 45 star by just a couple of days. And he said he had never been so happy to not get a medal in his life. For the war was awful, and countries and people were broken. In particular, he was impressed by the deep brokenness of Germany, not only of their physical country, but of their character, having suffered for more than a decade of Nazi poison. And so he chose to spend the remaining money he had from the war, and he and a partner bought as many German Bibles as they could and returned to Germany instead of coming home. They wanted to show that forgiveness was better than vengeance, that love was stronger than hate. They wanted to show unconditional love. And I hope one day to be able to understand the fullness of that unconditional love. He came home, married my grandma, had my dad and my uncle. I showed up. He was a wonderful grandpa, a wonderful great-grandpa, and he'll be dearly missed. And so thank you to the many Canadian service members who served. This is in memory of you. This is in memory of Private Ross Robinson, from your loving grandson. Know your history, know your physics.